Okay, so a couple more topics to cover. So we're going to start with standing sound waves. Okay, so there's really two ways to look at standing sound waves. We're going to cover waves going through a pipe with two open ends and waves going through a pipe in a pipe with one closed end. So first off, the thing you want to notice is so everywhere that you see a zero, that's a node. That is a wave node. Everywhere you see a maximum, that's an antinode. Okay, so you're going to have some similar equations here. So for this one, I went ahead and put your nu, your Greek letter nu equals your F. This is going to be your frequency. Okay, so for your standing waves in a pipe with two open ends, your frequency is going to be the energy level N times frequency 1. And then where your lambda of each individual, your wavelength of each individual energy level is going to be 2L over N. So L, of course, will be the distance the wave travels. So if you look here, you see a bunch of these. So it's like from here to here, that's a distance of L. Now, the thing to keep in mind is that your two open ends will account for every single energy wave because you're either going to have sound or you're not going to have sound. If you have an antinode at the end of the tube where the opening is, you have sound. If you have a node at that end, you have no sound at all. And so you see here, these, what's going to start happening is, I'm really not sure why they gave you the column on the right, but if you look at that column on the left, all of those are going to have their antinodes as they're reaching the ends of those tubes. So you can kind of start to take account of this if you say, well, I look at N equals 1, which is that very first one at the top. So there's N equals 1. You notice, so how much of the wavelength do we have all the way to L? So see, if we start up here, and then the wave passes through the 0 point, and we end up down here. How much of the wavelength is that?
Just one.
You know, half. So at L, we have 1/2 lambda, which leads to lambda is going to be 2L. You take a look at, say, N equals 2, you'll find that so okay, if you look at N equals 2, so we have there to there. How much of the wavelength is that? 1. Lambda equals L. N equals 3. So we're going to look at, we have here, there's a full wavelength, and we end up back on the bottom. How many ways is that? How many wavelengths? 1.5. So so your L would be 3/2 lambda, which means that your wavelength is going to be 2/3 of the length L. And you notice how these waves are getting more and more compacted as you go up in energy levels. So that's where, so when you put all that together, that's where you say, well, if I look at N equals 1, so lambda 1, you say that's 2L or 2L over 1, but it becomes more apparent if I say, well, lambda of 2, that equals L, or 2L over 2, so on and so forth, until you end up with your with your equation here, we see that the wavelength of your sound waves inside these open-ended tubes is going to be 2L over N. So N being your energy level. That you can feed into your frequency. So for example, why is frequency V over lambda? So V is the speed of the wave. What do we have? We have meters per second, meters. What is that unit? Hertz. So the speed of the wave over its wavelength gives you the frequency of your wave. Okay, so now this is where it starts to change a little bit. When you have your pipe closed at one end. So, what is a system in the human body that is represented by a pipe closed at one end?
Radius.
You don't. Sound waves in your trachea are super important. Here. You don't hear with your trachea.
Not bad.
It wasn't the right answer.
It isn't close too.
So first off, let's take account of a sine wave here, okay? So if we start here, one full wavelength is there, okay? So that means here, we get 1/4 lambda, here, half lambda, here, 3/4 lambda. Now let's see, that's lambda and 4/3. Okay, so that being said, we go here at n equals 1. At n equals 1, all the way over to L. How much of the wavelength is that? It's a fourth. I'm going to skip and go to n equals 3. So that right there. At L, how much do we have? So this one here, go to lambda, is for L. So what is L? So at L for n equals 3, what do we have? We're looking at that sine wave. So what we went here, 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 here.
That one.
Of course. And so again, if you follow this pattern through, you end up with the wavelength with this closed-end tube being 4L over N. Your N is your energy level. Your frequency is going to be N V over 4L, or so your 4L is, of course, your first frequency. So that's your first overtone. And then, of course, your energy levels for this one are 1, 3, 5, 7, 9, so on and so forth. Because let's think about it. That means your ear can only pick up every other overtone. What happens if I did like n equals 2? So if you look here, imagine that's the open end, open end, open end. What happens if I go to like n equals 2? You can node at the open end, which means you're not going to register that sound at all. The wave might still propagate, but you're not picking up that overtone. So that's going to be kind of a key for you. You need to know that on some sort of exam. Okay. This is funny. hollow tube, length of 1 meter, inserted vertically into a tall container of water, which means it's now closed on one end. Tuning fork of frequency 440 hertz is held above the hollow tube. If the distance delta L that the tube is moved between resonances, when you're going to these different overtones, is 39.3 centimeters. What is the temperature of the air inside the tube?
It's like one of those big questions they make fun of physics.
So there's a couple of things we have to figure out here. We need to know the distance between each resonance. How much of the wavelength? Okay, well, my delta L is 0.393 meters. So let's just take a look. Okay, so n equals 1. You remember that L lambda over 4 equals 3. L is force over lambda. So what is the distance between these two? These are two overtones that you're going to hear. Okay, so you have, so let's say, so the lambda, you have the 1/4 plus R gives you 3/4. 1/4 plus what gives you 3/4? 2/4, yeah. 1/2. The distance between each overtone is 1/2 lambda, or the distance between each resonance is going to be 1/2 lambda. Okay, so this means that the lambda that we're looking, so that lambda, that actual distance, L, that means it's going to be 2 of L equals 2 times 0.393. And now we know the distance between each resonance, how much of the wavelength. Now, velocity of a wave is what? The velocity of this wave is going to be what? What times what? Frequency times what? So it has to be meters per second. Frequency is 1 over seconds. Yeah, wavelength. Okay. So now we know that the speed of this wave Johnny, Chachi, physics class. Is that too old of a reference?
Yeah. The immediate yes.
So we're going to get a wave speed of 345.84 meters per second. Now, what do we use to figure out the temperature of a wave at this speed? Yep. So we have this. We don't know T. So let's see, we could say that E over T0 is going to be V over V0 squared. T is going to be T0. V over V0 squared. And then we remember from our references, so we have a reference speed at 0 Celsius. Okay, Okay, so this means that our T0 is our reference. The velocity of our wave is actually 345 meters per second over the reference speed. Rid of that. And you end up with a temperature of about 24.3 degrees Celsius. The multiple parts of the chapter in play. Okay, so that's the concept of standing waves. And thinking about each one of these resonances, these overtones as different energy levels. That means N is your what number? Discrete, allowed energy levels, N equals. It's too much to hope you guys remember chemistry class. That'd be your quantum number.
Oh, yeah.
Yeah, I would remember
What?
that.
Yeah, discrete allowed energy levels. Okay, another important topic, the Doppler effect.
Doppelganger?
Sheldon dresses up as that.
Yeah, he does,
As
doesn't
a
he?
Halloween costume.
So,
Doppler effect.
Can
What do they think he
someone
was? A
describe
zebra?
to me a time when you experienced the Doppler effect?
When I'm watching Big Bang Theory.
Huh? Yeah, that's why usually I always get tickets because I ask the officer if their radar has been calibrated lately to make sure that the calculations that it has to do to factor out relativistic effects are accurate.
Yeah. Just to let you know.
Do they?
Yeah.
No, not getting pulled over.
Just bring this guy around.
What's a time you've experienced the Doppler effect?
Can you explain it to me? I can't read that. Too far.
Yeah. The frequency you observed is going to be different based off if an object is coming at you or going away from you.
So like, can you standing still in a truck going past?
Right. You ever heard that, or have you ever heard a motorcycle come by? Or,
Yeah.
you ever heard an ambulance where the sirens are really high pitched when it's coming at you? They go past you. That's the Doppler effect. Because as it's coming at you, it's actually chasing the waves it emits, so it's decreasing that wavelength, making it higher pitch. As it goes away from you, it's moving away from the
Oh,
waves.
I understand his costume now.
Do you?
Yeah.
So as you go away from move away, the wavelength is
Still look
getting
like a
larger
murderer.
because you're getting further away from the source of emission.
Good show. I should start rewatching.
Okay, so let's say we have a moving observer. Okay. Well, your wavelength in this case
Not hour.
is going to be v t0. So that's the speed of the wave. So the distance the wave has gone. So the speed of the wave is sometime that the observer has observed. Minus the speed of the observer. And again, this is going to depend on whether you're moving towards or away. We'll talk about that when we get to the actual Doppler effect equation. And then remember that T is your period, so your time for your wave, your period.
Well, yeah, it did change now.
It's 1 over what?
It changed.
Your period is 1 over what?
Changed that semester.
So that means that now your lambda is V minus V0 over F. So the observed frequency. Remember, for this, your O and your S, your sub O, sub S is going to be observer, observed, and source. Okay? Because again, let's say we have a moving source, you get a very similar equation by the same arguments. Okay, your lambda is going to be the speed of your source, the speed of your wave minus the speed of the source over the frequency emitted by the source. Okay, so So when we put these together, we get the actual Doppler effect equation.
I don't wanna learn the equation. Come on.
So remember, O is observed, S is source. Your V here, that's the actual speed of your wave. And then you have to think the sign on your V of your observer and the V of your source are going to change their sign based off if you're moving towards or away from the source is moving towards you or you towards it, or you're moving away from each other. So when you're getting closer to each other, you have a positive sign. If you're moving away from each other, you have a negative sign.
So if they're both moving. But if only one of them's moving.
It doesn't matter. If one is moving, if both are moving, then you have accommodations for observer, for source. So it's like if only the source is moving, V sub O is 0. So now take a few minutes and work on this. See if you can get all the parts. Because I'll tell you, the first thing you have to figure out is the frequency emitted by the source. You don't have it. Remember, the chapters to study for your final are chapters 9 and 12. Fluids and sound.
Not 9 through 12?
No, not 9 through 12. If I did that, I mean, I could, but that would be naughty for me because we didn't do chapters 10 and 11.
Yes. I mean, I knew that from the chapter.
Does anyone want to do like 9 through 12?
No.
I don't want to at all. Don't make me. We're not doing this.
Huh?
Number 8.
Now we'll just leave rotational motion out of it.
Column.
Yes? Just make sure you bring your computer with you because we're going to do it quiz style. You'll be on Canvas, you're just going to open it up and like,
You know what I really liked that I think you should think about is the one quiz question that you did, where it's like keep going, the next one, if like everyone was kind of like that, like I think that's
you know what I love about questions like that is there's still people who get them wrong.
those are the people that don't read them. They just click
Yeah.
I thought that was fun.
So let's see, I'll tell you that it's 20 degrees Celsius, the speed of sound in air is 343 meters per second. Yeah, 20 degrees Celsius, the speed of sound in air is 343 meters per second.
Finding MS.
Yes, you have to have that first. You can't find the observed frequency if you don't have this. See, look here, you're using this equation. You'd have to find SS first. The first observed frequency is 212 hertz. Yes. So try to break this into the approaching car and the receding car. Have numbers for the approaching car. The frequency emitted by the source is going to be the same no matter what. What changes is the frequency you observe, whether it's coming toward you or moving away. That's going to be constant. Let's see. So V is going to be that speed of sound in air, so 343 meters per second. That's the actual speed of your sound wave.
I see.
I said it a few times.
Well, I'm saying
Yeah, you'd be given it in some way. It'd either be in the problem or on a table somewhere. This one's on a table in the chapter. Yeah. You could also figure it out by remembering that we've done a lot of problems with the sound and air. The reference sound and air is 331 meters per second at 0 Celsius. I just decided to tell you what it was at 20 instead of giving you the extra calculation. You have a battery.
what?
You have a battery.
Yeah, but it can also charge. Where's it at?
Psychological experience for it.
So hot.
Studying the effects of negative emotions on physics. And that's a reference to a movie from the late 80s. You know, most of you weren't around in the late 80s, so
Yeah, no, I was born in 2005.
yeah.
There.
Yeah, like the observers are not moving, so that was.
Yeah, so the observer's not moving.
Oh,
So the thing, 03.
Only the source is moving.
You said 05 and I'm born January 4th, 05.
okay, that makes sense.
That makes me feel so old.
Don't worry, it gets better.
I don't know if I wanna know.
I see high schoolers driving their cars now. I'm like, that kid's like 9. Why is he driving a car? He's not 9.
Said it went to my friends. I remember 07 baby. I was like, stay away from me. I was like,
You know, the frequency of the source is 199.5 meters. So let's look at it. So as the car is coming at you,
I got it.
okay? So we're gonna start. Now we don't know the frequency of the source. So the speed of the observer is 0, so we can take that out. Observe. Okay, so you have your 343 meters per second. The minus your 32.0 meters per second, the speed of the source, which we're going to leave as positive because they're getting closer to each other.
I'm not. An Ellery.
Times your 220 hertz. That's what you observed as it's coming towards you. Multiplying this all up, you're going to get 199.5 hertz is the frequency emitted by the source. The same source, so that frequency is going to stay constant. So now we say now as the car is moving away, we want to know what the new observed frequency is. We're still going to use the Doppler effect equation, but we know that V sub O is 0. We now know what that frequency of the source is. Except now they're moving away from each other, so the V sub S is going to be negative. So you have 343 meters per second over meters per second minus a minus 32 meters per second times your 199.5 hertz. As the car is moving away, you observe a frequency of 182.5 hertz. You see how the frequency has decreased. So that means as it's getting closer to you, the car has a higher frequency. As it's moving away, it has lower frequency. So the sound like pitch. You see, once you get your numbers straight, Doppler effect's not super difficult to work with. So moving away. V sub S has to be negative in your approach. V sub S is positive. You want to keep track of that positive and negative. So does Doppler effect seem pretty straightforward?
Can one of the questions be about Sheldon Cooper?
Could be. Just kind of think of it this way.
Was he a zebra or
As
the
you and the
Doppler
storks are
effect?
getting closer to each other, the waves are being smooshed, higher pitch.
No, the question is to be, was he a zebra or the Doppler effect? A zebra, that's what they kept calling him.
Zebra?
Yeah. They didn't know he was a Doppler effect.
I'm more interested in the old philosophical definition.
That is
Zebra
zebra.
white with black stripes or black with white stripes.
It's like that dress with a blue, black or white.
That I've never seen.
Oh, people like,
Yeah.
So,
it's kind of insane, like, I've never seen this.
It's weird.
War is over.
any questions?
No, but Sheldon Cooper versus, is he a zebra or the Doppler?
Done.